Hi, I'm Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I want to discuss about the numerical problems on lasers. So, previously we have seen about the applications of lasers. So, in different fields, we have seen that applications of lasers in medical field and industrial field, and then we have seen some scientific applications also in the previous session. Today we will see about the numerical problems of lasers. The problem, find the relative population of the two states in a ruby laser that produces a light beam of wavelength 6943 angstroms at 300 degree Kelvin. So this is the problem. So first we will write that what the data have been given in the problem. So the given data is wavelength and then temperature 300 degree Kelvin. But what we have to find, so from the problem we have to find the relative population of the two states, which is for ruby laser. Okay, so a relative population of the two states. So wavelength lambda is equal to 6943 angstroms, which we convert into meters. It will be 6943 into 10 power minus 10 meters. So wavelength has been given in angstroms that we are going to convert in meters. So 1 angstrom is equals to 10 power minus 10 meters. As 1 angstrom is equals to 10 power minus 8 centimeters, angstrom in meters is 10 power minus 10 meters. So wavelength in angstrom is converted into meters, that is equals to 6943 into 10 power minus 10 meters. And the temperature T is equal to 300 degree Kelvin. So we have to find the relative population between two states. So the two states are E1 and E2. So population between two states. So what is this E1 and E2? So these are the energy states, two energy states. The formula which is related to that is the population ratio N2 by N1 is equal to minus of E2 minus E1 by KT. Here N1 is the number of atoms per unit volume in the ground state A1. N2 is the number of atoms per unit volume in the excited state A2. But E1, where A1 is the lower energy state, E2 is the excited energy state. And the K is the Boltzmann constant. K is the Boltzmann constant that the Boltzmann constant value is 1.38 into 10 power minus 23. T is the temperature. T is the temperature. So these are the parameters in the formula. So population ratio N2 by N1 is equal to e power minus of E2 minus E1 by KT. So here we know that E2 minus E1, so the energy difference is equals to the energy of the photon. So the emitted photon is equals to h nu, which is equals to the energy difference between the two energy levels. Suppose this is the energy state E1, E2 is the excited energy state. So as we are discussing about the Ruby laser, so the atom in the excited state after the lifetime transits to lower energy level by emitting photon of radiation h nu. So this h nu is equals to is the energy of the photon. That energy h nu is equals to E2 minus E1. That is energy difference between the two energy levels. The energy of the photon is equals to the energy difference between the two energy levels. So E2 minus E1 is equals to h nu, that is equal to hc by lambda joules. So where here nu is equal to c by lambda. Nu is equals to c by lambda. When substituting mu is equals to c by lambda, so the energy h nu is equals to h into h into c by lambda, that is equals to hc by lambda joules. N2 by N1 is equal to exponential of minus of 6.6 into 10 power minus 34 into 3 into 10 power 8 divided by 6,943 into 10 power minus 10 into 1.38 into 10 power minus 23 into 300. So here the formula, once again I am writing here, N2 by N1 is equals to exponential of minus of E2 minus E1 by KT. So this is the formula. So we have to find this N2 by N1, that is number of atoms in the lower energy state. N2 is the number of atoms per volume in the excited energy state. So this ratio, this population ratio we are going to find. So that is equal to exponential of minus of E2 minus E1 by KT. So this E2 minus E1, here E2 minus E1 is equals to h nu, as nu is equals to c by lambda, we can write hc by lambda in joules. So the same we are going to substitute here, then the formula becomes exponential of minus hc by lambda divided by KT. As this can be simplified, exponential of minus hc by lambda K2. So now we shall substitute the values of these parameters. As we know that h is the Planck's constant, and this Planck's constant value is 6.626 into 10 power minus 34 joule second, where c is the velocity of light. So the velocity of light is 3 into 10 power 8 meters per second. And K is the Boltzmann constant, 1.38 into 10 power minus 23. And T is the temperature. So Planck's constant h is equals to 6.626 into 10 power minus 34, as I have written here 6.6 as Planck's constant. So 6.6 into 10 power minus 34 into C is 3 into 10 power 8 divided by lambda. So lambda, which we have converted into meters, so 6,943 into 10 power minus 10 into Boltzmann constant B, this is lambda, and the temperature 300. So 6,943 into 10 power minus 10 into 1.38 into 10 power minus 23 into 300. So the value of N2 by N1 is equals to 8 power minus, that is exponential of minus 69.3. So exponential of minus 69.3. When calculating this exponential of minus 69.3, we'll get this solution, the answer, that is 8 into 10 power minus 31. This is the population ratio of the two states in the Ruby laser. Next, we shall go to the next problem. For helium neon laser, at 1 meter and 2 meter distances from the laser, the output beam spot diameters are 4 millimeter and 6 millimeter respectively. Calculate the divergence. So the given data in the problem is distances. So the distances from the laser. So distances from the laser, let it be D1 and this is D2. So D1 is equals to 1 meter, D2 is 2 meters. And laser spot diameter, the output laser beam spot diameters, or A1 is equals to 4 millimeter, A2 is equals to 6 millimeter. So which is converted into 4 into 10 power minus 3 meters. A2 is equals to 6 millimeters, so that is equals to 6 into 10 power minus 3 meters. Now we have to calculate laser divergence theta. So the formula for laser divergence is theta is equals to A2 minus A1 by 2 into D2 minus D1. So A2 minus A1, let's substitute 6 into A1, A2 is 6 into 10 power minus 3 minus 4 into 10 power minus 3 divided by 2 into 2 minus 1. So it is equals to, here I am writing. So A2 is 6 into 10 power minus 3 minus 4 into 10 power minus 3 divided by 2 into 2 minus 1. So this value is 6 minus 4 into 10 power minus 3 divided by 2 into 1. So that is equals to 2 into 10 power minus 3 divided by 2. So this is 1 into 10 power minus 3 radians. So we can write this as 1 milli radian. So laser divergence is equals to 1 milli radian. Next one, a helium neon laser emits light at a wavelength 632.8 nanometers and has an output power of 2.3 milliwatts. How many photons are emitted in each minute by this laser when operated? So the given data is wavelength of the laser beam lambda. So lambda is equals to 632.8 nanometers. So the nanometer, 1 nanometer is equal to 10 power minus 9 meters. So 632.8 nanometer when converted into meters, 6328 into 10 power minus 10 meters. That is lambda is equals to 632.8 nanometers. So 632.8 into 10 power minus 9 meters. So when taking out this point, so 6328 into multiplying with, so 10, so minus 10 meters. So the output power, is 2.3 milliwatt. So the milliwatt is converted into joule per second. So that is equals to 2.3 into 10 power minus 3 joule per second. So we want to calculate the number of photons emitted per minute. So formula for this power output power P, which is denoted with P. So P is equals to NH mu. So where the parameters are, these parameters are, P is the output power, N is the number of photons emitted. H is the Planck's constant. Nu is the frequency. Nu is the frequency. So we have to calculate this number of photons emitted. So that from this equation, N is equals to P by H nu. Output power by H nu, frequency of the energy of the photon. So N is equals to P by H nu. So where nu is the C by lambda. So when substituting C by lambda instead of nu, P by H into C by lambda. This is equals to P by HC by lambda. That is equals to P into lambda by HC. So that N is equals to P lambda by HC. So energy emitted per minute, that is the output power per minute, P is equals to, as we per minute means we have to take that is we have to multiply this output power into 60. So that energy emitted per minute, we are taking the output power energy per minute. So that P is equals to 2.3 into 10 power minus 3 into 60 joule per minute. So let's substitute all these values in the formula. N is equals to P lambda by Hc. So where P is per minute they have asked in the problem. So 2.3 into 10 power minus 3 into 60 minutes into lambda 6328 into 10 power minus 10 divided by H is Planck's constant 6.626 into 10 power minus 34 into C is the velocity of light 3 into 10 power minus 3 into 10 power 8 meters per second. So the value of this is N is equals to 4.3949 into 10 power 70 photons per minute. Next one, solve the wavelength of emitter radiation from gallium arsenide, which has a band gap of 1.44 electron volts. So the data given in the problem is energy gap of a semiconductor of gallium arsenide. So Eg is equals to 1.44 electron volts. When converting into joules, as we are using the formula energy gap, Eg is equals to H mu. So that Planck's constant we are going to take in joules, so that we have to convert in joules. So 1 electron volts is equals to 1.6 into 10 power minus 90 joules. So multiply with 1.6 into 10 power minus 19, the energy gap of a semiconductor, gallium arsenide semiconductor, it is equals to 1.44 into 1.6 into 10 power minus 90 joule. So we have to calculate the wavelength of emitted radiation. So formula, energy gap of a semiconductor Eg is equals to H nu. So from this we are going to calculate the lambda. So in this Eg is equals to H nu, nu is C by lambda, so Hc by lambda. So Eg is equals to Hc by lambda, so we want lambda, so lambda is equals to Hc by Eg. So H is the Planck's constant, C is the velocity of light, energy gap already given in the problem, which is 1.44 electron volts. So now we wanted to calculate the lambda value. So lambda is equals to Hc by Ag. So H is 6.626 into 10 power minus 34 into velocity of light 3 into 10 power 8 divided by 1.44 into 1.6 into 10 power minus 90. So the value of this lambda is equals to 8633 into 10 power minus 10 meters. Another problem, a semiconductor laser diode has a wavelength of 1.55 micrometer. Estimate its energy gap in electron volts. So the given data wavelength lambda is equals to 1.55 micrometers. So micrometers can be converted into meters. 1 micro is equals to 10 power minus 6. So 1.55 into 10 power minus 6 meters. So wanted to calculate energy gap of a semiconductor. So the formula for energy gap is equals to G is equals to H mu. So that is equals to Hc by lambda, where H is the Planck's constant, that is equals to 6.626 into 10 power minus 34. C is the velocity of light, 3 into 10 power 8 meters per second. So let's substitute all these values. Eg is equals to Hc by lambda, that is equals to 6.626 into 10 power minus 34 into 3 into 10 power 8 divided by 1.55 into 10 power minus 6 into 1.6 into 10 power minus 90. So the value of the energy gap in electron volts is equals to 0.8 electron volts. So we took all the values in joules. So here in the final expression, when dividing with 1.6 into 10 power minus 19, it can be converted into electron volts. If we write 6.626 into 10 power minus 34 into 3 into 10 power 8 divided by 1.55 into 10 power minus 6. So this value gives in joules. But when we are dividing with 1.6 into 10 power minus 19, it will be in the electron volts. So when dividing with 1.6 into 10 power minus 19, it can be converted into electron volts. As in the problem, they asked us to estimate its energy gap in electron volts. So that we divide with 1.6 into 10 power minus 19 electron volts. So these are the problem which are related to the lasers. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.